Hello physics students. In this video, we're going to be deriving the formula for the capacitance of a spherical capacitor. Now just a reminder that a capacitor can be any two chunks of metal. You charge these chunks up oppositely charged, one positive, one negative, and then they attract each other, and you could utilize that attraction by connecting a wire from one chunk of metal to the other and allowing electrons to flow, and thereby releasing work or energy to do various tasks. So we already studied parallel plate capacitors, and we derived a formula for the capacitance of two metal sheets that are parallel to each other as our capacitor. Now, we're going to do that for, as I said, spherical capacitors. In other words, one metal sphere within another metal sphere, and the spheres are charged up oppositely. We're going to be following the same process. Remember, there are 4 steps to that process. Can you name those 4 steps? If I were to ask you to close your eyes, can you think of those 4 steps in your head? Well, you should, because those are the signposts that help you with these derivations. If you can remember those 4 big steps, then you can follow them for parallel plate capacitors, spherical capacitors, and cylindrical capacitors. So think for a moment if you could think of the steps. Okay, well, if you couldn't remember the steps, well then, after today, make sure you study those steps so that they're strong in your memory. Here they are. So we got our spherical capacitor. We've got, as I said, one sphere, radius A, another one, a shell with an inner radius B and an outer radius C. Maybe we charge the inner one positive. We could have charged it up negative, but we charge it up positive in this instance. And we hooked it to the ground. Remember, this is a schematic representing a wire connected to the earth. What will happen is the earth, this positive will draw a certain amount of electrons from the earth to charge this metal the opposite charge. So this minus came from the earth, drawn toward this positive. The negatives will all deposit themselves on this inner surface, thereby making the electric field 0 inside the metal here, which is true of conductors in static equilibrium, as well as outside the conductors. So the electric field only exists in this region here. Okay, so now the 4 steps. The first step we do is we start with C equals Q over V, the definition of capacitance. The more charge you store for a given voltage, the higher the capacitance to store charge. So in order to determine what the capacitance is, we've got to get rid of V, which means first or second, we calculate the electric field. We use Gauss's law, we make a Gaussian sphere around this, and we want to find the electric field in this region inside of our capacitor. So then the left side of Gauss's law, E times the surface area of our Gaussian sphere, which is 4 pi r squared, and the Q enclosed is just the charge of that inner sphere, okay? And then we solve for E, there's the expression. All right, if you need a moment to catch up, I'm going to create a pause to allow you to catch up. Okay, let's move on. So now that we have the electric field, again, we want to get voltage. So we get delta V between these two conductors, which is always defined as minus the integral from one point to another of the electric field that lies along a path as we move from one sphere to the other. So we put in our formula for electric field. I just rewrote it in a different form. I put all the constants together here, and then the r squared, I took it out of the denominator and made it to the power so that it'll ease the integration process. The limits. Why did I go from B to A? Well, ultimately what we want, capacitance, it doesn't make sense for it to be negative. It's always got to be positive. And so knowing that this conductor is positive in here, we know that the electric field points away from it like this. This is the direction of the electric field. So what we want is to put in a positive voltage to get a positive capacitance, means we've got to integrate uphill of the electric field against the direction of the electric field. It's like gravity. If I go against the force of gravity, I go to positive potential energy change. When I go with, I go negative. So I integrate against from B out here into radius A. Now this just integrates with the power rule. Add 1 to the exponent and then divide. And then my limits, I plug in my limits, put in A first, then B, as you know we do with integration. What I'm going to do is I'm going to find a common denominator. It makes it easier later. So the common denominator is A times B. So if I multiply the top and bottom here by B, then I haven't changed the factor here, this fraction. Multiply the top and bottom here by A over A. And what I get is B minus A over AB. And there is the voltage. So that was the third step. Finally, we plug it into C equals Q over V, and we get our expression. So here's the voltage plugged in that I got. And then I could flip this fraction up to the numerator by turning it over, which I did over there. You see the Q's go away, and there's my expression for the capacitance of a spherical capacitor. All right, if you need a moment, I'll create a pause to allow you to catch up. Okay, so there it is, the 4 steps. Again, when you go back and look at these notes, make sure you know those 4 steps. The next thing I want to do, one last thing. Now, I've been saying over and over that a capacitor is 2 metals oppositely charged. And most of the time that's true, but sometimes you can think of one metal object as having a capacitance also. You might be thinking, well, where's the second metal for the charge to go from one metal to the other to release that energy? And the second metal, in a sense, the second object, is infinity. In other words, if I charge a metal up negative, I could also allow or create electrical energy by just taking a wire and stretching it out to infinity. And then the electrons are just going to go that, against the electric field. And so they'll go to infinity and release energy in the process. So in a sense, one sphere alone has capacitance. With infinity, the other place where the charge can then go. So what we could do is we could find the capacitance of a single isolated sphere by using this formula. And I'll show you how. So what we do is we take this C formula that we got and let me just write it out. So okay, so we take this formula and we imagine that that outer shell gets bigger and bigger and bigger and becomes infinite in size. What does this formula become then? So that would be, again, a shell with the other one being out at infinity. So in order to determine what our answer is, we could do this. We could multiply the top and bottom here by 1 over b. And I haven't changed anything. And so what it changes in the formula is the top becomes this, and the bottom becomes b over b, or 1 minus a over b. And now what you could see is that if b becomes infinite in size, this part of the formula becomes 0, and the capacitance of a single isolated sphere is this. Now, this is smaller than the capacitance here, because if you look, here's that 4 pi epsilon 0a, then we're multiplying by b over b minus a, which is a number or a ratio greater than 1. So this is bigger than that. So the capacitance gets smaller. It's the smallest value for that sphere in that if it's just one sphere isolated. So if you need a moment, I'll allow you to copy this. I'll create a pause to allow you a chance to copy this down. Okay, now one last thing I want to mention. One reason why this is important is because we'll talk about it more with circuits, but if I stick a piece of metal into an outlet, and even if I'm isolated, I have rubber shoes, I still receive an electric shock. And the reason why, we'll learn that there's no place for the circuit to be completed, but what's happening is that electricity is charging and discharging me as a capacitor. So as that electrical energy is oscillating in a typical wall outlet, it's charging me and discharging me. That creates an electric shock because I have a capacitance, even if I'm standing alone isolated. All right, so that's spherical capacitance. I hope you enjoyed the video. I'll see you in the next physics. Oh, before I sign off, I just want to remind you, can you name those 4 steps for deriving capacitance? When this video ends, if you can't think of what those 4 steps are, rewind the video and or look over the notes and familiarize yourself again with those 4 steps so you'll be ready for the coming test. All right, I'll see you in the next physics video.